This lesson is for Chapter 5, Section 3, Properties of Logarithms. Again, you're going to want to have your calculator handy, and then our books need to be open to page 383. All right, the first thing that's discussed in this section is change of base. We talked about this a little bit in class today, but most calculators only have log buttons, which are base 10, or ln natural log buttons, which are base e. So if the problem involves some other base, we use change of base formulas to compute. Now, I know that the calculator has a function that does take care of that to you or for you to an extent, but you're going to have to be able to do that independently of the calculator as well. So make sure that you don't neglect figuring out how to do this without the tool or the device in your hand. All right, so these are roughly the formats, and you'll notice that they all look very similar to each other. If you have log base a of x, all you end up doing is setting the log of x over the log of a. So whatever these two numbers are, hang on here, I'm going to straighten out my pens real quick. They're about 2 inches off. Sorry, hang with me. Whatever these two numbers are, your base here as well as your x here, the log of x is divided by whatever the log of a was. All right, so that's what essentially all three of these are telling us. So in checkpoint problem number 1, if you're looking on page 383, it says to evaluate log base 2 of 12 using the change of base formula in common logarithms. So if we're using common logarithms, we're doing the regular log, not the ln, but we would set this one up simply as log 12 over log 2. And if you punch those two into your calculator, you end up with, now when I punched mine in, I went with log 12 and then I just hit divided by log 2. Okay, so you don't have to figure them out separately because they are decimals. So if you chop them off and then do your division second, you might end up being a few thousandths or hundredths off from what the key is. So this seemed to work just fine for me. Evaluate log base 2 of 12, same numbers, using the change of base formula and natural logarithms. Well, it's really not going to look a whole lot different here. We're still going to take the natural log of x, which is natural log of 12, and divide it by the natural log of 2. And we still end up with that same number value, 3.585. Okay, so just a little practice on how to maneuver through your calculator. Now these next properties here are pretty straightforward, not too hard to understand. We have first the product property, which says if we have log base a of uv, u times v, that's the same as log base a of u plus log base a of v. The natural logs work the same way. So natural log of uv equals ln of u plus ln of v. The quotient property, so if we have log base a of u divided by v, now it's just subtraction of the two. Okay, same thing for our natural logs. Our third property is the power property. If we have log base a of u to the n, that's the same as saying n times log base a of u. And again, it works the same if you have your natural log. Okay, so those are going to be used often today. These would be ones that you might maybe want to highlight so that you can come back to them quickly and make sure that you're comfortable with and can follow them. So taking a look at this one. All right, so this is one of those cases where using your calculator is not going to help you out here. Write each logarithm in terms of log 3 and log 5. So when we look at example A, log 75, we're going to try to rewrite that number as a combination of 3s and 5s. All right, so when I think of this one, this is what I did first. I looked at it as 3 times 25 because then I was able to get at least the 3 in there. And then looking at the other factor, the 25, I rewrote that as a 5 squared. So now when you have that product property of 3 times 5 squared, we can rewrite that as log of 3 plus log of 5 squared. Now using another property, we can get rid of that exponent so that we just have a log of 5. So leave your log of 3 alone, that one's good to go. But that power can come out front. Again, if you need to, look back to those previous properties on the previous 2 slides. So now we have that problem rewritten with log 3s and log 5s. All right, so B, we're going to do the same kind of thing. So if we have log of 9 over 125, that's that quotient property. So this would be rewritten first of all, at least this is what I did, log of 9 minus log of 125. Okay, then I started rewriting my numbers so I could get in those 3s and those 5s. So 9 can be rewritten with 3s, and 125 can be rewritten with 5s. And again, we don't quite have log of 3. We've got 3 squared, but that power comes out front. Same thing with the 5 to the 3. Bring the 3 out front. And we have an equivalent value. Checkpoint number 4. Find the exact value of natural log e to the 6th minus ln e squared. All right, so again, remembering our properties, if we have a power, that power can be brought out front. So I'm going to rewrite ln of e to the 6th as 6 ln of e. And I'm going to do the same thing for the second one here. That would be rewritten as 2 ln of e. Now, in your chapter, it tells you what the natural log of e is equal to. ln e, natural log of e, is 1. So again, this is going to be one of those things, being the wording of the problem, I would anticipate seeing one of these on that page where you're not able to use your calculator. So being able to realize or remember some of these relationships is going to be necessary. Rewriting log expressions. Look through example 5 in your book. Okay, example 5 takes us to page 385. When you have many things going on in the expression part of our logarithm, okay, being able to break them apart and listing them singly is going to be something that you're going to be asked to do. So it's called expanding the expression. So what we have here for this checkpoint problem, it says log base 3 of the quotient 4x squared over root y. So a couple of things here first of all. Our logs generally don't keep any square roots. So I'm going to first rewrite, leave that alone for a second, but change this into y to the 1/2 power. Okay, so we worked with that way back at the beginning of the year, and that's something that can be done. Then we have a product, and we also have a quotient. So I'm going to start pulling those things apart. I have a log base 3 of 4 times x squared. Log base 3 of 4 plus log base 3 of x squared takes care of that. And then we also have the divide by y to the 1/2. So I'm going to do then the minus part for the quotient. Okay, so I've just picked those things apart. Now the book didn't do this, but in my head I feel like I almost should be, so that we know exactly what the top is going to be and what the bottom underneath all of that's going to be. Now we can take a look at, is there anything else that I need to get rid of? Well, a couple of these pieces of our problem have powers yet on our x's and y's. We're going to get rid of them. So log base 3 of 4 is good. But then on this one, bring that power out front. 2 log base 3 of x. This subtraction part here, the denominator from the original one, has a 1/2 power. Bring that out front. And there's your expanded form. We can also condense. So maybe they give us a stretched out one. We can rewrite that in a condensed or a shorter form. So let's take a look. First of all, you guys on your own look through example number 6. They have 3 of them that are completely done out for you in your book. Okay, so follow them along. Remember things like square roots being equal to 1/2 powers of things. Might have to refer back a couple slides to those properties again. The more of these you practice, the better you'll get at them. When I went at this one, I left the initial part alone because this log with the x plus 3, you know, there was no number in front of log, not inside the bracket anyway. But on the second half of that, there was, where you have the 2 in front of the log of x minus 2. So that was the first thing I rewrote. I took that 2 from out front and I put it behind as a power. Okay, now the 2 out front goes to each of the things that are in that bracket, correct? So the next thing I did was I distributed. So now I have 2 log of x plus 3 minus 2 log of x minus 2 squared. Okay, so I distributed my 2 to both of those pieces inside my bracket. Now I'm not going to leave that 2 out in front. So this front one, this first part, I'm going to rewrite with the squared. And on the second part here, I'm going to again take that 2 out of the front, and it's going to get tacked on to my power, which now will make a power of 4. Now the last thing I can do to condense this, because this is a minus in between these 2 pieces, that could be undone or condensed using my quotient property. So I could go log, whoops, not frog, log x plus 3 squared over, whoops, x minus 2 to the power of 4. And condense it like that. Where do we use these logarithms? All right, I talked with a few of you in class today about that. One way that our book takes us into as to where in the world would we ever apply this is the application problem on page 386. When XY data is nonlinear, okay, so in other words, maybe it forms a scatter plot where there's a correlation, either positive or negative, with our numbers. We know that sometimes when we graph data, we end up with those scatter plots rather than something that's truly linear. We can find how they are related, those XY points of our scatter plot, by taking the natural log of each of the x and y values. If these points fall on a line, you can conclude that the values are related by the equation natural log of y equals m natural log of x. Notice how similar this is to y equals mx, and then there's just no b in back, but it's linear, okay, where m is going to be the slope of our line, just like m was the slope of our y equals mx plus b lines. Okay, so take a look with me at the checkpoint problem for number 7, which follows example number 7 done in your book. Both of these kind of operate in the same fashion. So it says, find a logarithmic equation that relates y and x for the following ordered pairs. So if you were to take the 5 points that were given as they are and graph them, they're not going to line up. All right, if we take these points and find the natural log of each, so I'm using my LN button, you end up with this table of values, and I'm just going to go ahead and I'm going to write them in an XY chart. So I took this one first, and I did ln of 0.37, and then I did ln of 0.5. When I did so, I got this for x, ln of 0.51 gave me this. Natural log of 1 is 0. So the second point ended up being 0, 0. The third point was 1 and 0.668. Then 2 and 1.332. And then my last point with the 20.09, it was awfully close to 3.2. Okay, so play with your calculator, punch each of those XY values from our data list in and find their natural logs, and you'll see these digits that I've just put in the table. Now these are graphable. Okay, so that first point is roughly -1 and close to -0.5. Then we have 0, 0. Then we have 1 and 0.668, 2 and 1.332, 3, whoops, going the wrong way here. Come back. Let's try this and this. I don't know what I was doing. And this. Now 2 and 1.3-ish, and 3 and 2. But do you notice how they actually line up? Now to find the equation of that line that lines them up, pick any of your 2 points and come up with a slope. Okay, just because 0, 0 actually end up in my table, I use these two. Okay, so my slope between these 2 points, you've got 0.668 minus 0 all over 1 minus 0, which is 0.668 over 1, or 0.668. So I can write an equation with the ln of y being equal to, here's m, that's my slope, 0.668 of ln x. Okay, and there you go. So I suppose if we were looking at a relationship of data and trying to create a model or some kind of a tool that we could use to make maybe predictions or whatever based on, I don't know what this data even would have come from. This one was something about, you know, the box in the example 7 in the book came from distances with planets. So this is one relationship that I find that went, huh, well, yeah, I guess that is kind of useful. And I remember conversations with Mr. Torgerson where he was referring to this, and now I know what he was talking about. So do what you will with that, but it's not a very hard thing to accomplish. Taking the natural log of those ordered pairs and then graphing the points and coming up with the equation of the line, that kind of gets us back to some Algebra 1 stuff, and that's always a good thing. All right, so your problems are going to come from the next following pages. We've got 387 to 389. Repetition is the key. I need you guys to do a lot of these. Don't take the weekend off. Do a bunch, get comfortable with them, and we'll be looking at a quiz now that we've done sections 1, 2, and 3 coming up real soon.